Swayam Prabha. Digital India. Educated India.
Hello, welcome back to today's discussions. We'll continue on discussing on the dicyclopentadiene zirconium species formation and how they are utilized for the strategically for different synthesis. Okay. In the last class, we have seen the reactive metal fragment that is used for the dicyclopentadienyl zirconium species formation. Today's oxidative cyclization discussions mainly will focus on at first discussing how to generate dicyclopentadienyl zirconium species from an alternate method, namely the beta abstraction method. Once briefly discussing that, then we will move to titanium isopropoxide tetra isopropoxide method to give the titanium diisopropoxide reactive intermediate and to utilize it for oxidative cyclization reaction. Subsequently, we will see the cyclobutene ring formation and then we will try to move in the end of it, we will try to move to the other metal mediated transformation that we will see for this course. So, in the first part, let us see how one can generate cyclopentadienyl zirconium species directly without undergoing the reactive metal fragment that we were discussing in the last class. Okay. So, the beta abstraction method for cyclopentadienyl zirconium species formation. Of course, this is unsaturated version. So, what we can do is we can take cyclopentadienyl zirconium chloromethyl and take the lithiated intermediate, let us say we can have any cyclic intermediate or a cyclic intermediate, does not really matter. Overall, the main thing is it has to be lithiated and we can then synthesize the zirconium this intermediate where this cyclic intermediate is part of the zirconium species along with this, then we will get the methane formation from there. Overall, this is a beta position, it is not a beta hydride elimination, but the beta abstraction, because zirconium is in +4 oxidation state. For beta hydride elimination it will not be possible, and then therefore, it undergoes the beta abstraction to give out the methane, this two part, and directly it forms the complexes of high energy species, that is for example, with benzene or so we can get the zirconium intermediate, right. So, for example, if it is a benzene, you can put overall benzene formation from here on. So, from this intermediate we know that this is cyclopentadienyl zirconium benzene intermediate formation, right. So, this is a method which avoids the intermediacy of reactive metal fragment, as we have seen in the last class. Also, it allows the preparation of complexes of high energy species such as benzene. This benzene species formation one can see by this method. Also, it solves the problems of chemo and regioselectivity that were appearing in the last discussions, as we have briefly looked upon. So, once again, this is a beta abstraction method to prepare the cyclopentadienyl zirconium species. Previously, we have seen that dicyclopentadienyl zirconium dichloride, for example, was reacted with organolithium, N-butyl lithium, for example, 2 equivalent of it, and from there on dicyclopentadienyl zirconium species, unsaturated one, was synthesized. But today what we have seen is it is an alternate method of preparation of the cyclopentadienyl zirconium species, which is much cleaner, and it can gives rise to the cyclopentadienyl zirconium unsaturated intermediate quite efficiently, and therefore, those similar application as we have seen in the last class, even for natural product synthesis, this dicyclopentadienyl zirconium species can be used. Moving on, these oxidative cyclization reaction. Now, we would like to discuss the titanium reagent. So, titanium tetraisopropoxide reagent are the starting material. From there on, so diisopropoxy titanium reagent can be generated, but how they can be generated and how they can be applied strategically for organic synthesis is the next point of attraction for this course. Let us discuss the titanium reagent. So, we will be discussing the hybrid mode, hybrid titanium isopropoxide and the Grignard reagent combination to give the diisopropoxide titanium reagent. So, we will be discussing titanium O isopropoxide and then isopropyl magnesium halide, for example, reagent for generating different titanium reagent which can be utilized for further organic transformation. Let us say, for example, we have titanium isopropoxide 4, and we are reacting with 2 equivalent of isopropyl magnesium chloride. Overall, what we will get is that titanium diisopropoxide intermediate along with this diisopropyl unit that is coming from here, right. So, overall we will get this intermediate first. From there this isopropane will go out, and then a cyclobutane, titanium containing cyclobutane ring will be generated. So, one of the H, so the beta abstraction, namely beta abstraction from this CH3 will give rise to the isopropane, or in this case simply propane, and then we will get this 3-membered intermediate with the metal in it. So, Metallacycle will form, and 2 of the isopropoxide will be attached to it. This is nothing but, if you look at very carefully, this is nothing but the olefin coordinated titanium diisopropoxide, right, diisopropoxide intermediate. Now, this is the intermediate from where we can get rid of olefin if we want. For example, if we wanted to react this intermediate, let us say this is an intermediate int. Okay. Now, this intermediate, if we want to react with an alkyne, and we can then react and then get the cyclopropene type of intermediate, titanocyclopropene intermediate we can get. Let us see how this intermediate that we generate right now with this isopropyl magnesium chloride reagent, how this can be utilized further to incorporate a new reagent or make them reactive under the reaction condition. Let us look at that. Okay. So, we are taking that intermediate, if you remember, that was having the propene associated with titanium with 2 diisopropyl oxide. Let us say take that intermediate and then react with another alkyne, for example R prime, this alkyne. Overall, then what we will get, that olefin will go out, and this 3-membered titanium intermediate will be formed, and this will be then reactive towards a number of species that we will be seeing. So, similarly, this species, as you know, is similar to this dicyclopentadiene titanium reagent or the zinc or the zirconium reagent that we were discussing. Now, this intermediate from here on, for example, if we are interested in reacting with another aldehyde, this aldehyde will be able to interact with this 3-membered Metallacycle, and overall then into this aldehyde double bond, this cyclopropene will be able to insert, and then the final species that we will be getting in this case is a 5-membered intermediate, where we have for example C6H13 and TMS, if these are the R and R prime we are taking, and from there on we can get the cyclohexyl. Of course, cyclohexyl we can get, and cyclohexyl overall it is giving a 5-membered intermediate from which iodine can react to give the open chain. So, this is more of an electrophilic attack on this 5-membered Metallacycle, and from there on we have the reaction with iodine to give rise to the olefin in product that one might will be interested in synthesizing. Overall, cyclohexanaldehyde is incorporated in the form of cyclohexanol, and then we do have the olefin incorporated into the ketone. So, this is a nice oxidative cyclization reaction. As you can see, we started with an aldehyde, we started with an alkyne. It is the combination of alkyne and aldehyde that gives rise to the final product. Alkyne part, you have seen it form the olefin with the iodo in it, and the other center of the alkyne is now associated with an aldehyde to give you the secondary alcohol. Now, these are the powerful technique to synthesize a number of interesting molecules. Specifically, if you are looking for a retro analysis, you can rely on this method quite confidently and can deliver the desired product quite efficiently. Let us look at some of the similar type of reaction as we have seen in the last class in imine type of chemistry. In this case, we will be taking an imine along with an alkyne to form the cyclic product that is similar to what we have seen in the last class. So, we will be seeing these the reactivity of these titanium reagent. Let us, for example, one example we will be having. So, various imine containing one along with an alkyne appended to it. If we are reacting with that titanium intermediate, so that we have drawn previously, how to generate it, we have seen it from titanium tetraisopropoxide. Overall, this process will give rise to the this propene intermediate will go out, and this will react, titanium reagent will react with the imine to give you the 3-membered intermediate with the titanium and nitrogen in it. That is a very interesting intermediate, isopropoxide 2. Along with it, there will be this alkyne that is associated with it. Overall, from this intermediate, we then will be able to get the oxidative cyclization will give rise to the another 5-membered intermediate in addition to what we have seen in the organic fraction, and this 5-membered intermediate will then can be reacted with another electrophile very confidently, and it should be giving the final product beautifully. Now, this is the reaction reported by Sato in 1995, and lot of application has been planned based on the synthesis of these 5-membered organic molecule with various electrophile in it. So, in this example, what we have seen right now is the titanium reagent, that cyclopropane type of reagent. So, it is a 3-membered titanium reagent that Metallacycle now have reacted with an imine, okay, where olefin goes out and imine is now coordinated oxidatively with the titanium space with the titanium center. Now, that titanium nitrogen containing intermediate will be reacting with the alkyne in situ, which is sitting within the substrate to give rise to the cyclic 5-membered organic intermediate, and then from there on we can add an electrophile to finally get rid of the titanium reagent from the product. Overall, then this can be seen as the true manifestation of the oxidative cyclization processes, where versatile organic compound can be synthesized rather easily. And then we will be also discussing further on these processes, not only these these organic molecule, simple organic molecule with the 5 to 6-membered, 7-membered ring even can be synthesized. We can see that various heterocyclic synthesis can be also planned by utilizing this technique. This is a clever application of the pyrrole synthesis, which is utilizing this titanium reagent for this oxidative cyclization processes. Overall, we will see quite a few rearrangement to come up with the pyrrole synthesis in presence of carbon monoxide as the reagent. Let us look at that pyrrole synthesis. So, pyrrole synthesis by using this titanium reagent. Well, we can have from an alkyne, we can have these overall these 3-membered titanium intermediate with isoprop oxide species in it. Now, as you have seen previously, it can react with an imine. So, for example, R4 and R3, these are the 2 reactive species if we are taking. As you can see from the oxidative cyclization technique, we will get the 5-membered titanium reagent along with the as a ring over there. So, overall if you look at it, is a fully substituted version of this titanium isoprop oxide reagent. Subsequently, if we are reacting with carbon monoxide, 1 atmosphere of it, under 1 atmosphere carbon monoxide, this carbon unit will be incorporated over here. So, overall we have 1, 2, 3 carbon, another carbon from this carbon monoxide, and upon further rearrangement we will see the pyrrole ring formation is going on quite well for these reactions. So, for example, if we have R3 here and R2 here and R1 here, this carbon is coming from the carbon monoxide. Well, it is overall what you will see that carbon monoxide is inserted into this titanosin reagent to give rise to the 6-membered intermediate. From there on, extrusion of this carbon monoxide oxygen to the titanium center overall will give the product. So, what now we have seen then, from an alkyne and an imine, we can put together an alkyne and imine along with carbon monoxide to give the pyrrole. The 4th carbon in the pyrrole is coming from the carbon monoxide. Quite an interesting rearrangement reaction that is involved. After this 5-membered titanium Metallacycle intermediate, we will see the carbon monoxide insertion and then extrusion of the oxo or the oxygen atom from the carbon monoxide on the titanium center to give you the titanium oxo species, finally gives rise to the rearranged product that leads to the pyrrole synthesis. Let us look at the pyrrole synthesis mechanism by utilizing this technique. So, overall it will, from this 5-membered intermediate, will have a 6-membered carbon monoxide containing species, where we will see that substituents are quite efficiently placed beautifully, R1, R2 and R3 and R4. Overall, this titanium isoprop oxide then can be involved, and as you can see, this is overall will be a rearrangement reaction where the 5-membered intermediate now will be forming to give rise to the pyrrole backbone, and these substituents are in the correct place as we want them, and from there on the titanium 3-membered intermediate with the oxo in it can be synthesized quite easily by utilizing this technique. Subsequently, we can have titanium oxide released from this intermediate to give rise to the desired product. Now, these intermediates are quite efficient in synthesis of the pyrrole, and high yield of pyrrole can be generated from this species. So, this is the final species, and from there you get the substituted pyrrole and quite efficiently. Even in the yields are usually very high, 60 to 90% yield can be obtained. This is reported by Sato. Of course, R1, R2, R3 and R4, this carbon is from carbon monoxide. Now, this is once again a very beautiful and clean synthesis of pyrrole, starting from an alkyne and an imine. So, alkyne 2 substituent and imine 1 substituent will be there, and pyrrole nitrogen is coming from the pyridine from the imine, and the extra carbon that is required for pyrrole synthesis, that is indeed coming from the carbon monoxide, where titanium reagent will be capturing the oxo to give the titanium oxo, where carbon from carbon monoxide gets into the pyrrole cycle to give the final product. Now, this is utilized quite well for pyrrole synthesis. Now, we will see this titanium reagent for natural product synthesis or the fragment of the natural product synthesis. Let us look at briefly two such examples where these titanium reagent are used for natural product synthesis. Well, we will be first synthesizing the model complexes of mitosine. So, synthesis of mitosine models, mitomycin models. Well, the reagent that we need can be prepared quite rather easily, and this is reported in JACS 1997, where we have this advanced intermediate. We see that olefin and the keto is rightly placed, and if we are able to bring a suitable reagent, for example, titanium reagent, we can start with this titanium cyclopropane type of intermediate, which was generated from the cyclopentene intermediate. So, let us say over here, overall we can get rid of this cyclopentene intermediate, and from here on titanium can move on. Of course, titanium O isopropoxide is over there. Titanium can move on this olefin, and it can form a 3-membered ring as one would expect, and this oxidative cyclization is once again very efficiently done. And as you can see, there is another keto that is right now sitting very close to this titanosin reagent. From here on, this keto reagent can be reacted with this metallocyclopropane ring, overall giving rise to an intermediate that will have the 4 rings together formed along with the Metallacycle intermediate. Then subsequently what we will see that the oxidative cyclization between this 3-membered ring and the ketone will give rise to the cyclic titanium intermediate, which will be very efficient in opening up with oxygen, finally giving rise to the product, where of course the substituent benzene substituent are there in the right place, and overall we can get the dihydroxy intermediate, which is a mitomycin model quite efficiently, and the yield was up to 60%. So, what we have seen right now is in presence of an olefin and a keto, which is juxtaposed, placed beautifully within one molecule. It is an intramolecular reaction we are trying to promote, starting with the titanium reagent, titanium diisopropoxide unsaturated version of it. If we are reacting with it, initially of course the olefin reacted to give the new titanosin intermediate with this 3-member intermediate with titanium in it, that can then cyclize with the ketone overall to give rise to the 5-membered ring, which can then ring open to give to react with oxygen. So, therefore, the dihydroxy intermediate can be generated quite efficiently by utilizing this technique. We will then move on to synthesize some various version of this sort of oxidative cyclization reaction. For example, next we will be discussing the application of this method for some few more organic molecule synthesis. So, we will be synthesizing then cyclobutene. So, catalytic cyclobutene formation we will be then focusing on, which will be again very interesting for the organic chemistry perspective. So, strategically the cyclobutene reagent can be generated, which are otherwise very difficult to synthesize. So, we will look at this catalytic cyclobutene formation by utilizing this oxidative cyclization technique in a moment. We will not discuss many examples of it, but main mechanism of the cyclobutene formation will be discussed in conjunction with the oxidative cyclization processes. Let us go on catalytic cyclobutene formation. Well, the reagent that is required for it can be an alkyne halide. With it we can have, for example, now dicyclopentadienyl zirconium chloride, which is used quite efficiently, and a Grignard reagent 3 equivalent of it in presence of, let us say 10 mole percent of the cyclopentadienyl zirconium reagent. Overall, it is a very beautiful reaction that gives rise to the cyclobutene by utilizing the simple reaction condition at THF in THF at room temperature. So, overall this is a powerful technique where you will see in a moment that the dicyclopentadienyl zirconium reagent is forming a 3-membered ring, which can then react with this reagent to form the 5-membered zirconium intermediate. From there on, further rearrangement will give rise to the cyclobutene formation. So, this is a once again a very powerful technique for synthesizing this cyclobutene ring, where it is an alkyne halide. Alkyne halide is reacted with dicyclopentadienyl zirconium reagent. We can have the zirconacin, this 3-membered zirconacin intermediate, for example, by reacting it with Grignard, for example, ethyl magnesium halide, which can give rise to the cyclopropane type of intermediate, where zirconium is in there in the 3-membered ring, and from there on reacting that with the alkyne halide we can get the product. Okay. So, we will come back with the mechanism of such reaction for the cyclobutene synthesis in the next class. Till then, please keep studying the oxidative cyclization reaction and the application of this oxidative cyclization reaction in organic synthesis. We will continue in the next class discussing on the cyclobutene, and we will also start discussing mainly the Poisson-Khond reaction by utilizing a similar technique of oxidative cyclization process. Till then, bye bye, see you next class.